I'm going to talk about applying the this idea of this electric energy, this next order energy Fn, to analyzing the dynamics for systems with Coulomb interactions. Okay, so I want to think of dynamics of the form for instance, of a gradient flow. Okay, where Hn is the original energy. I remind you maybe. Okay, it's defined like this. And this is the, the mean field regime where each particle feels an average force generated by the other particles. And as I told you on the first day, we want to understand the convergence of the empirical measures that are evolving in time. We want to understand what is their time-dependent limit, and that is equivalent to propagation of chaos. Another thing that you may want to do is consider conservative flows, where instead of doing the gradient, you apply an antisymmetric operator. So you can put, in fact, here some sort of matrix. And the condition on the matrix is that basically it's negative, as a symmetric matrix, right? So you need this condition. So for instance, minus identity is the case we have here. Satisfies this. Okay, so the first order of business is to sort of guess what this mu t should be, at least formally. And there are several ways of doing the heuristic derivation, but maybe let me give you one, which is that, let's say you have a Dirac mass at a point that is moving, delta x of t. The question is, what is the time derivative of this Dirac mass in the sense of distributions, right? So it means if I test against the test function, what do I obtain? So you can do it. It's a computation. Take a test function. And you find that this thing is equal to minus the divergence of the time derivative of x, so the velocity, times the Dirac. Okay, so this is always true in the sense of distributions. This is an example of a continuity equation. A continuity equation is something that gives you the evolution of some probability density in the form dt mu plus divergence of v mu equals 0, where v is a velocity field. Essentially, it's the thing that's pushing your distribution, your density mu. Right? So you're pushing mu in the direction of v. You solve this PG. Is that, are those things sort of natural? Yeah. Okay, so if we base ourselves on this, we have to understand for the empirical measure, we're going to have to sum things like this, right? So we're going to sum over all points and divide by n. And so we have to guess what is this effective velocity that drives each point. But so if we look at it here, the effective velocity is going to be the gradient of this thing. Right, so here we expect v to be equal to what? So we divide by n. and we take the gradient. So there's going to be this matrix M. So I take the gradient with respect to the variable I, but here that just picks up the gradient of G. And here I take the gradient, it's just grad V at xi, and there's no sum here. Okay, so basically this would be Vi, the velocity of the particle I. It's not even we expect, this is true, right? So we have Vi equals this. And now we want to sort of average this out. So what we're going to do is say that the sum over all the j's here, I can replace it by the integral against the density mu. Right? So I want to say that I want to use the fact that this, I can approximate it by mu. And so the velocity, I'm going to approximate it by m grad G xi. And now instead of summing over these j's, I'm going to just integrate over mu. Okay, so I replace this summation and divided by n by an integration. So I'm sort of already saying that this thing has averaged out. The distribution of points has averaged out to mu. And then the n simplify here, and I just get plus grad V, okay, of xi. So now this is here, there's some approximation. This is not exact, there's an approximation. But for each xi, I expect this, and so I expect that the velocity field as a function of x is just equal to this, which is what? So it's m. Here you see a convolution. So this is in fact the same as the gradient of this function h mu plus v. So the m should be in factor. Plus grad v. And now this is for every x, and you remember that h mu is the convolution of G with mu. Okay, so this velocity field, you see, is given by the gradient of the potential generated by the charges plus the external potential. So that's the gradient of the total potential. Okay, so physically this makes a lot of sense. This is the force, or that the particles feel in some sense, right? So you have the gradient of the total potential, and if you plug that into this, the continuity equation now, which I call here now the mean field equation, should be dt mu plus divergence m, so grad G convol mu plus grad V times mu equals 0. Of course, with initial conditions. And okay? Yes? All right, so sometimes people call this the McKean equation, or in quantum mechanics would be called Hartree-Fock. You can also do this with noise. I will discuss the case with noise at the end, so you can add some diffusion here. And if you add diffusion, you're going to pick up an extra 1 over theta Laplacian mu type term. So now the question is, can we make this rigorous? Because here there is a passage that was this wiggly sign, and it's actually thrickier than that to make a proof. So when G is regular, right, if you consider particles with regular interactions, say Lipschitz interactions, and maybe with noise, with or without noise, this has been understood for a long time. So there are classical methods due to Dobrushin, Makin, Snitman. You can follow the particles' trajectories, and you can derive this, this type of convergence. But for some, in fact, for a long time, things were stuck when we have singular interactions, which is our case, right? So the Coulomb interaction in particular was not accessible except in 2D where it's the log. Okay, the log is singular, but not very singular. But for instance, in 3D, this was open. And one of the techniques that people have used, so I said there's this trajectorial methods, and there's also methods that rely on finding a good metric to quantify the convergence. So let's say, so let me write what this means. Yeah, so finding a good metric means I have a distance on probability space, and I want to study the difference between this empirical measure, the distance between the empirical measure and the expected limiting density. Okay, so this is my time-dependent empirical measure, and this is my expected limit, so the solution to that PDE that I erased. Okay, so maybe you're lucky and there is a distance such that when you differentiate in time the distance, you find something negative maybe. So if that was the case, you would be happy because it would show that if you start initially very close, so little o of 1 close in n, then you remain very close. So that's a bit too much to hope for, but another thing you can try is to bound it by itself. Okay, so to bound this by the same thing times a constant. Because if you can do that, then you can apply Grunwald's lemma. Right? So Grunwald's lemma tells you that then the distance is going to be bounded by some exponential Ct times the initial distance. And that will mean that, okay, if this initial distance is small in n, then at later times you still have a small in n distance. Okay, the distance will grow in time, but for a fixed interval of time, it's enough to get convergence. So this is sort of the roadmap, a possible roadmap. And this has been applied in particular with Wasserstein distances. So for instance, W1, or there's a W infinity version of the Wasserstein distance that have worked for some class of singular interactions, but not quite as singular as Coulomb. Okay, so now today the message is going to be that a good distance for our problem is the Fn distance, which is not exactly a distance, but we saw yesterday that it's kind of like a distance, right? And that's why it became called modulated energy, because now we're going to look at Fn of x and t, mu t. And so you see the second slot here is going to be something that changes in time. So that's why it's modulated in time, if you want. So it's a bit like when you look at a relative entropy method, right? You look at the relative entropy relative to a time evolving distribution. Okay, so I'll discuss also at the end the relative entropy method and how it's been how it works well to treat problems with temperature or with noise. Okay, so the first little calculation I want to show you is it's another calculation that shows basically this type of relation, but at the level of the limiting PDE. Okay, so if you want to hope that something like that is true, a good test is to try to see whether it holds when you take two solutions of the limiting equation. So what is the limiting equation? I remind you. So if you allow me, I'm going to drop the V from now on. I'm going to look at a problem without the external potential because it's simpler, and also a lot of the results are proven only in this context. So I'm going to do V equals 0. It's not so important. No problem. And so we have, let's say we have this equation. And we want to consider two solutions. I'm just checking that the sign is correct, because sometimes easily make sign mistakes on this. Yeah. Yeah, it's maybe there's a minus. This is why I always need to check. Yes, it's minus. Thank you. Okay, so let's say you have mu1 and mu2, two solutions now. Or mu1, mu2. You'd better hope that if mu1 and mu2 are initially close, then they remain close at later times. Because after all, the empirical measure, you want to think of it as an approximate solution to your PDE. It doesn't really solve that PDE, but it approximately solves it. So if you want to show that the empirical measure being close to an initial measure, they can't drift too far apart, it better be true for two solutions that are initially close. Okay? Not equal, but close. And so let's see whether they remain close. And as I claimed, a good metric is this Fn distance. But for two solutions, okay, what is Fn? You know, Fn, as we have seen, in the Coulomb case, we can think of it as this, just grad Hn squared. So where Hn was G convol with some delta xi minus n mu. So if I want to transfer this back to a continuum setting where I don't have Diracs, here what we're going to take is we're going to take d equals, so it's going to be the square of a distance. I'm just going to do grad h mu1 minus h mu2 squared. It would be exactly the equivalent. So this is the potential generated by mu1 minus the potential generated by mu2. I take the gradient and I square. So this is my justification. Now I could just pull this out of a hat and tell you I'm going to consider this. Okay, so it's exactly the same, actually, in the Coulomb case as G x minus y, d mu1 minus mu2 of x, d mu1 minus mu2 of y. This is also the same. So up to constants, something like that. CD. Yeah.
A quick question on the assumption on the V. since we assume that V is equal to 0, do we still know that the empirical measure converges to the equilibrium measure since there is nothing confining the charges?
Yes, you're right, there is nothing confining. And so the equilibrium measure is not really in the story now because you're going to start from an initial condition, and in large time your particles are just going to spread. They're just going to spread indefinitely. If you had the confinement, then you would think you converge to the equilibrium measure, but in large time. Okay, but what you care here is not so much where you arrive in large time, but how you evolve. So I just want to derive the dynamics. If you put back the V, yes, you expect that you're going to converge to the equilibrium measure, although it's not so obvious that there could be other stable situations, etc. But yet, from the point of view of random matrices or things like that, it's better to add confinement, quadratic confinement. Okay, so I'm going to look at this Coulomb distance, you see, which is like this total interaction between charges mu1 and charges minus mu2. And now it's defined like this. And let me demonstrate for you that it works at this level. So we're going to differentiate in time. Grad h mu1 t minus h mu2 t. So my two solutions in time. And so it's just a computation. Okay, so you get grad h mu1 t minus grad minus h mu2 t. There's a 2. And now we have to put dt. So gradient dt. And I can integrate by parts. So I can put this gradient here into a Laplacian. I don't have to worry about terms at infinity because the things have the same mass. So the potential is going to decay at infinity. Its derivatives decay also sufficiently fast. So we find ourselves with something like this, h mu1 minus h mu2. And when I put the Laplacian, and I hit the h with the Laplacian, you see the nice thing is that the Laplacian of h is the measure. So up to constants, this becomes dt mu1 minus dt mu2. And there are those constants, so there is a minus Laplacian, and there is just a CD here. Let's hope that my signs are correct. We'll see later if they are. Okay, so this is not looking too bad because now this is the time evolution of the time derivative of the density. We have a formula for this because we assume these things solve this PDE, so I can plug in the formula. Grad h mu1 minus grad h mu2. And now reintegrate by parts. Right? I minus, thank you. Signs are important here. And integrate again by parts, 2CD. So we get grad h mu1. Actually, I don't want to integrate by parts yet. Let me see. I think I should first do something else. Oh, no, I integrate by parts. Okay. Okay, so we get there. So now comes a new object, a new quantity, which is called the stress energy tensor. So this is a thing that's not coming out of nowhere. In calculus of variations, in mechanics, it has a physical meaning also. So physicists call that, well, that's why it's called stress energy. You can hear the physics in there. This is an object that happens, that occurs when you encounter it when you take a variational problem and you try to make perturbations that are diffeomorphisms of the domain. So basically, you're taking your system and you're pushing. So just to give you an idea, when you have a function u of x, you can make variations like I showed you the first day of the form u plus tv, right? So it's like you're perturbing in the target. And now, if you take variations of this form, it's a different kind of variations. You're perturbing in the domain and not in the target. And you're looking at the derivatives in t of these types of variations. What comes out is the stress tensor. Okay, so it's the object that you find when you make these types of, they're called inner variations. But okay, I'm just going to give you a definition. So given some h here, I'm going to, function h, I'm going to define grad h. It's a tensor, so it takes two indices I and j going from 1 to n. And it's going to be 2 dih djh minus grad h squared delta ij. So you know the symbol delta ij, it's the Kronecker symbol. So it's just 0 unless I equals j. And so this is the tensor. If you want, you can put it in matrix form, right? So if you put it in, for instance, in 2 by 2 form, so in 2D, it would be of this form. So you're going to have 2 d1h minus, so you have d1h squared. Here you would have 2 d1h d2h, 2 d1h d2h, sorry, d1h squared minus d2h squared. And here you'd get d2h squared minus d1h squared. That would be the sort of form of your matrix. Okay, so that's a quantity. And now what we do is we compute its divergence. So it's you see this matrix is symmetric. So you can compute either the divergence of the rows or the divergence of the columns. So what I mean by divergence is I'm going to pick, for instance, I, and I'm going to do the sum of the derivatives with respect to 1 to d, di, and j remains a variable. Okay, so it still depends on j. So if you want, the divergence is a vector, right? It's a vector. Okay, so now there's an explicit computation you can make. You have to compute that di of this. So you see, you're going to take derivatives of products like that. So you apply the product rule many times. And I'm going to give you the answer because this is just a completely direct computation, which is that the divergence of this, which is a vector, is equal to 2 gradient of h times Laplacian of h. It's not so surprising you get a Laplacian, because you see you're going to hit di, you're going to get 2 derivatives, and then you're going to sum, so it's going to give up. Okay, so this seems plausible, and it's actually a direct calculus. So maybe my coefficients might be off. I think it's a 2. And there is this, yeah. I think it's a 2. Okay. All right, so now what's nice is that if we apply it to our functions, to our potentials, h mu, right, h mu, what do we obtain? We obtain gradient h mu. And now we take the Laplacian of h mu, so that is mu, up to minus 2 CD. Okay? So the whole point of this computation is that it allows you to reinterpret these types of product. Gradate h mu, h mu. And interestingly, we see them here. They're actually what's sitting in the PDE here. Okay, so this product, you can express it as the divergence of something. It's always interesting in math when you can express something as a derivative. Right? One of the benefits of that is that if you have a measure which is not so regular that you can apply the product rule here, we apply the product rule, we're assuming things are differentiable. Well, if you can't apply the product rule, you can still start to give a weak meaning to this product as a divergence. Because this thing, you see this thing here, that's always defined as long as the gradient is in L2. Right? So this is always bounded by gradient h squared pointwise. So there's a 2 maybe. But okay, so this is pointwise bounded. So you can always give a meaning to that in L1 as long as this integral is convergent. So this has a meaning, and as a result, now this starts to have a possibly weak meaning. Okay, so what I'm going to do now is I'm just going to substitute, but I'm going to have to modify this a little bit before substituting. And let me erase. Okay, so this dt that we were computing is equal to 2 CD so I can do that. And now I'm going to rewrite this as grad h mu1 minus mu2. Sorry, grad h, how do I want to write it? Mu1 minus mu2. This way things dry a little bit. Yes. Right, h mu1. Right, I would like to rewrite it like this. Grad h mu1 minus grad h mu2, mu1 minus mu2, but it's not correct. So I have to add terms to correct. So I have grad h mu1, mu1, minus plus grad h mu2, mu2. So I'm going to add plus grad h mu1, mu2 to correct. Plus grad h mu2 mu1. This is not good. What am I doing? Okay, let me rewrite this a little bit. Okay, I can write it like this. Minus. The minus. Okay. So there's a minus in front of that. No. Okay, so some of my signs are wrong somewhere. Yeah, my signs got wrong. I don't know where. It's supposed to be a minus sign here. So here is a minus. So here should be a plus. And then maybe here when I integrated by parts, I made a mistake. Okay, anyway, it should be a minus. And so this way you get a plus. No, you get a minus. Yes, you get a minus. And then you correct by saying it's grad h mu1 mu1 minus mu2. That's funny, I can't do this thing again. Okay, I'm just going to copy my notes. It will work better. So we have grad h mu1 minus grad h mu2 with a minus sign multiplied by this product. And this is equal to so this one is going to come with a minus sign. So grad h mu1 minus mu2 mu1. And then minus integral grad h mu2 dot grad h mu1 minus mu2 mu1 minus mu2. Okay, so we have to check that this is correct, but okay, so we have grad h mu1 mu1 minus grad h mu2 mu2, which gets subtracted from this one. Okay, so it's this. Okay, so it's just a rewriting of this difference of things. And now what is good about this is that the first term has a sign, because you can recognize it like this. And the second term, here you recognize the stress tensor. So a product of this form for mu1 minus mu2. So it's minus this dot divergence of the stress tensor for mu1 minus mu2. And so the first term is negative. It's very good. I can drop it. And this came from the fact that it's a gradient flow. So it's a dissipative equation. So it decreases energy. So I did it for the gradient flow. If you had the general flow, you would have an m here. But this would still have a sign. And now, when you see the stress tensor, this divergence, you integrate by parts again. And so you get basically derivatives of mu2 times this. But this you can pointwise bound. So what I'm going to do is I'm going to bound pointwise this by a universal constant times the sup norm of the Hessian of h mu2. And this I bound pointwise, like that. So I bound pointwise by its integral of grad h u1 minus mu2 squared. And so what we have obtained, this is, you see, this is the thing we started from, this grad h mu1 minus mu2. So we obtained this when we differentiated in time we differentiated in time this, we obtain that this is less than C times this L infinity norm times itself. Okay, so this is my D, and this is the D again. So the conclusion of that is that if you apply Grunwald's lemma, if you assume that this thing is bounded, uniformly in time, or at least for some interval of time, then you can apply Grunwald's lemma and conclude that the solutions are close if they are initially close. Okay? But there is an assumption, right, which is that one of the two solutions has to be quite regular. So this is called a weak, strong uniqueness principle in PDE. Okay, a weak, strong uniqueness principle is something that says if you have one solution which is strong, so it has derivatives that are controlled, etc., and you have another solution on which you don't know regularity, it's a weak solution. If they are initially equal, they remain equal. Or here you can say it's a weak, strong stability principle, because if they are initially close, they remain close. Okay, so near a strong solution, there is a sort of attraction of all other solutions that remain close. And so that is good, because now what we want to do is we want to apply with mu1 equals the empirical measure. Okay, it's not really a solution, but we can think of it as a weak solution. And mu2 equals the limit. And so we're going to have to assume that this limit is regular enough. It has these two derivatives that are bounded. Okay, but that's a PDE question. Okay, we want to show it things converge to a solution up to a certain PDE. Now question, does this PDE have smooth solutions? So you give that problem to a PDE specialist, and you ask them, okay, can I assume, assuming that maybe initially my initial distribution is very regular, can I say that at later times I'm going to have many derivatives? And it turns out that for the Coulomb case, the answer is yes. So if you start from initial data, which is nice, you can prove that the solution later is nice. And so it now becomes reasonable to assume that this is bounded on a fixed interval of time, and now you can finish with Grunwald. Okay. All right, so now what we have to do is we have to replace this computation by a renormalized computation, because you understand that when we deal with the true empirical measure, there are Diracs in there, and the integral of grad h squared is no longer convergent, so we have to give it a meaning in a renormalized way. And so the way to go, okay, so for the true problem, what we're going to do is we're going to differentiate in time the Fn itself. So that's the replacement for that quantity. Okay, so assuming that x and t solves the ODE, and mu and t solves the mu t solves the PDE that got erased, but you saw it before. All right, so there's a computation to make. You differentiate in time, you compute, you compute. So I'm going to give you the answer to the result of the computation without having to do it. It's just completely, there's nothing, there's no thought to put, just compute. And you find that this is less than minus 1/2 double integral So this is this matrix M. Dotted with grad G x minus y. Okay, so let's say sum of Diracs at xit minus n mu t, and then you tensor this x and y. And you remove the diagonal as before. Okay, so this is the thing you obtain. At first, it doesn't look great, but we're going to see what to do with it. Okay, so first of all, here, what you recognize is these are the velocity fields. Right, so this is something of the form v of x minus v of y. Okay, this is my velocity field, dotted with grad g x minus y Okay, so it's something of that form. And now I'm going to forget that these things are evolving in time. I'm just going to think, okay, given some configuration of points, given some measure mu, I forget about this whole dynamics business, and I look at this type of quantity. And the theorem is, basically there is a functional inequality which tells you what you want. What do you want to know? You want to know that this thing is bounded by Fn itself, so that you can apply Grandval. Right? If you can show the time derivative is bounded by itself, you can apply Grandval. Well, the theorem says, indeed, if V is Lipschitz, I can bound by C times the norm of grad V times Fn. And there is a little additive error. Well, it's not so little, but it's actually not so bad. Which is a quantity we've seen before, the n 1 plus s over d. And then there's also the n log n in the case s equals 0. Okay, so for every xn and for every mu that's bounded, this inequality is true. And we call it a commutator estimate because hidden behind it, from the point of view of analysis, there is what's called a commutator estimate in there. Okay, so this is pure analysis now. Just it's a functional inequality you have to prove. And now I hope that you can be convinced that if you assume this inequality, then things are convergent. Because now what matters to show convergence is that Fn divided by n squared is small. Right? Remember, Fn is like a metric. So you want to show that Fn divided by n squared is much less than 1 as n goes to infinity. But this inequality tells us precisely now that we can get that dt Fn is less than c Fn plus n 1 plus s over d. But if you divide by n squared, right, you get just some little o of 1, which is even quantitative if you want. Because s is less than d. I even told you we're in the Coulomb case, but to simplify, we're in the Coulomb case, so s is certainly less than d. And now with that, you apply Grandval's lemma, and you get convergence, provided you have this bound, right? You need this thing on grad v L infinity. But that's exactly the same story as before. It's exactly the same as asking that h mu t has two derivatives which are bounded. It's the same condition. So it's a condition on the solution to the limiting PDE. And so we get a corollary, right, which is the convergence theorem that what we wanted is true as n goes to infinity over some fixed interval of time, provided that mu t is regular enough. Okay, so that answers the mean field limit question. Because, as you remember, Fn over n squared quantifies weak convergence. You can have some Sobolev space norm if you want for this convergence, for instance. Okay, so I should tell you a few words about what's hiding behind this functional inequality, the commutator estimate. Why, it's again a proof with the stress tensor, because the claim is that this thing is in hiding the same as what I was showing you before. By the way, you can observe something. G is singular, right? It's an inverse power, let's think. So when you take the gradient, you get the inverse power with an extra power. So instead of 1 over x to the s, it's 1 over x to the s plus 1. But on the other hand, you have v of x minus v of y in front. So if v is Lipschitz, this is bounded by x minus y. So when x and y are very close, right? So the singularity of this thing is actually the same as the singularity of G. Because you have 1 over x, s plus 1 times x. So it's like 1 over x minus y to the s, like G. So it's plausible that this thing is actually similar to f, because f is the same when this is replaced by G, right? G x minus y. So if you had G of x minus y there, you would have f. However, it's not quite that. So it's plausible that the inequality is true, but you can't really do anything directly like that, because here you have a lot of compensations happening. You have pluses, minuses, and if you start to bound, with absolute values everywhere, you're going to kill your compensations, and you can't really prove anything. So that's why the proof is a bit more subtle. However, I wanted to show that it's plausible. Okay, so what can we do? We can split this double integral thing into this. Okay, so I write this, and then I write the same with v of y. Okay. But when I write with v of y, there is a symmetry when you swap x and y, right? When you swap x and y, g doesn't change. So grad g gets changed into its opposite, but there is a minus in front. So in fact, you get exactly the same term. Okay, so the left-hand side is equal to 2 times that by symmetry. By symmetry of reversing the roles of x and y. Okay, good. And now here I can start to see a convolution. Because you see now I have a y, I have an x minus y. So I'm going to rewrite this as a single integral of v of x dot grad h. So it's going to be a potential generated by, okay, there's a mu here. And then, okay, all of that of x. So you see, this is of the form. So let us call Fn, maybe, this difference. So this is 2 integral of v dot grad h Fn. And h Fn It's what I used to call, yesterday I called it just Hn. There's no square here. All right, so we've transformed this expression, the left-hand side, into this. And so here I recognize again a product that's of the form of a stress tensor. So if I could replace this by the divergence of the stress tensor, we would be more or less done. But the problem is always this thing about the diagonal, right? You have to worry about the Dirac. So what you want to do, I'm not going to do it in details, is you want to do this with the truncated charges. So we want to write this whole thing. Right? We want to write this whole thing with the truncated charges. And then put truncated charges here, truncated charges here. And here now it becomes HNR, Laplacian HNR. And now I can rewrite this as 2V div grad HNR grad HNR. You remember R is this thing of the minimal distance for each point, right? The nearest neighbor distance divided by 4. So if I have this, I can bound pointwise by the Lipschitz norm of V. And remember, the stress tensor is bounded pointwise. Like this. And now we appeal to something I told you yesterday, which is that this quantity, with the truncation at level R, we can bound it directly by F. It's really legally, so there was an inequality yesterday that you can bound this by F plus, this extra additive error. But that is true. And that will almost make a proof, except that I cheated. I replaced the initial problem by a different one. I put the truncated thing. So there's an extra step, which is you have to compute the difference between the true left-hand side there and the one with the truncated charges. Okay? And the difference between truncated, untruncated, you can estimate it. And you estimate it using exactly these types of estimates I told you yesterday. You control this, and you also control that, if you remember, by F. So if you use all these controls, you can prove that this difference can itself be controlled by the same quantity. So there's a little bit of, okay, this takes like a couple of pages to look at all the terms in the difference, and also it's in the notes. But the bottom line is what I told you. So crucial ideas. Use Fn as a metric to quantify the convergence. So Fn is almost a metric. When you differentiate in time Fn, you see these weird terms that appear that are called these commutator terms. And then we have a functional inequality that bounds these terms by Fn itself, plus some errors that are actually small for what we want. Then apply Grunwald's lemma. Okay. So this is called a modulated energy method, because this Fn in this dynamic context is called modulated energy. And now let's talk about the situation with noise. So this works whether it's the gradient flow or these conservative flows. Say proof. So with noise. So we want to consider now the same thing. So this is a gradient flow, but we add some, so I'm going to call the inverse temperature theta, because in fact it's convenient to take it to be the same theta that I was talking about before. And we have these IID Brownian motions for all the particles. So if you had a regular interaction, or in fact if you had no interaction, it turns out that a very good quantity. Oh yeah, so you want to show that you converge to this thing, right? I'm going to write it again. dt mu equals minus divergence grad h mu t, and now there's a 1 over theta Laplacian mu t, if I'm not mistaken. So a very convenient quantity to metrize the convergence, as I was mentioning before, you want to find a good distance or something that is like a distance. In this context, with noise, a very good quantity is the relative entropy. So now we're going to let Fn t be the law of the SDE evolution. So basically Fnt x1 xn gives you the probability that at time t you observe the configuration at a certain location. And the relative entropy is going to be computed to be relative to some given mu, but in fact you should take mu t. So first, we define. So in the normalization that I've been using, I'm going to put an n in front, but typically there is no n. It's just because I multiply everything by n squared. Okay, so you want to take the integral of the log Fn divided by mu tensor n times dFn. So the result is that if Hn, call it Hn, and I divide by n squared just because this is in agreement with my other normalization. So if this goes to 0 as n goes to infinity, then you have convergence of the marginals of Fn, so fixed k-point marginals converge to mu tensor k times, or if you prefer, the empirical measure is going to converge to mu. You have total variation convergence. I mean, you have the standard convergence results from the relative entropy, right? So the relative entropy controls is a form of distance. Okay, so if you can prove that this is small, you're done. So same idea, right? Let's differentiate in time. Now let's take mu t, Fn t. Let's differentiate in time, and let's try to hope that you get some negative terms and something that you can control by the relative entropy itself. So in particular, So if, as I said, if you have regular interactions, this works actually quite well. And this was pushed to its boundary in a work by Jabin and Zhenfu Wang. Zhenfu was here. They showed that this works as long as G, okay, so I think more or less is this class, right? So it's a class, this is written in negative Sobolev norms, but basically this means that G is the derivative of something bounded. No. So it's grad G, that's not, yeah, it's grad G. Okay, so more or less G bounded is what you're asking here. So okay, it doesn't work for Coulomb, but it works for relatively reasonable. You can do the point vortex system in 2D with this by rewriting the interaction as the derivative of something bounded. But okay. All right, so then if you want to treat the Coulomb case or the Riesz cases that I was describing, there is now a good way to do it, which is called the modulated free energy method, and which was introduced by Bress, Jabin, and Wang. Which consists in observing that what you should do is not look at the relative entropy or not look at the modulated energy Fn, but you should combine the two. So there is something that's called a modulated free energy, which is defined as, so in my notes, I think I call it calligraphic F. Yes. Calligraphic F and theta of Fn relative to mu is going to be defined as 1 over theta times the relative entropy plus the expectation under Fn of the big Fn. Okay, so this is like expectation under the law Fn of big Fn. So what happens is, when you differentiate in time the relative entropy, you get some terms that involve, that look like this. They involve Laplacian gx minus y, you know, a bit like the terms I had before. But with this even worse singular kernel, like the Laplacian of g, you know, if g is singular, Laplacian of g is even worse. So you don't quite know what to do with those terms. You can't control them nicely by the relative entropy. When you differentiate in time this part, so Fn, or the expectation of Fn, you get Ito terms now, you know, because you have the Brownian motion, right? dwi. So you're differentiating something that's like integral of g, x minus y, blah, blah. The Ito terms are going to bring you Laplacians. So in fact, you see new terms that come out that are exactly of this form. And you don't know what to do with them because you can't really control them. But the beauty of this is that if you add these two things with exactly this factor in front, you actually get the same singular terms, but with opposite signs, and they cancel. Okay, so these terms here exactly cancel when you make the right combination. All right, so from the point of view of statistical physics, this is maybe not completely a miracle. There is a reason for this, which is that this thing has exactly the structure of a free energy. So that's why it's called modulated free energy. What is a free energy? The free energy is, you remember Gibbs variational principle that I told you on the first day, right? Gibbs variational principle says you should minimize the integral of the energy plus 1 over theta times the relative entropy. Right, there was something like that. So a free energy is something that has the addition of an energy, but okay, I should not call it H here, but maybe F. An energy plus inverse temperature times an entropy. So this has exactly this structure. 1 over theta times an entropy plus an energy, except that it's a relative energy and it's a relative entropy. Right? They are relative to a certain reference mu. But okay, so then the structure of this thing is sort of explained. And now you can make the computation. It's an exact computation. And again, I'm going to give you the result of the computation because it's not. It's particularly tedious, I must say, this one. When you compute, so if you take the solutions to your SDE system and mu t, the solution to the PDE, and you differentiate in time, the singular terms cancel, and you're left with other terms. And the first one of them has a sign. And you can actually rewrite it after some sort of observation. You see that it can be rewritten in a very nice form, which is a relative Fisher information form. So it's of this form. And there's a second term. Second term has exactly a commutator form. Okay, call it Vt of x minus Vt of y. So it's again the velocity field associated to the PDE. Okay, so what is this Qn beta mu? You may have forgotten from yesterday, but Qn beta was the sort of Gibbs measure, but when you consider the energy F. So here there is a theta, in fact. And there's a normalization that I call Kn beta, which is the partition function. And here you have the reference measure, d mu, in product. Okay, so when we did the splitting formula for the Coulomb gas, we found that, in fact, Pn beta can be rewritten as Qn beta of the thermal equilibrium measure. But we also could define this for an arbitrary mu. And we call this the modulated Gibbs measure. So it's the Gibbs measure, but relative to this mu. And the thing that's the term here that has a sign can be rewritten here as this thing is a It's called a relative, or it's the Fisher information, or relative Fisher information of Fn relative to Q. And what is V here? V is the velocity field. So it's grad h mu beta plus grad log mu t, and there's a theta somewhere, 1 over theta. Okay, so when we differentiate in time, we obtain these two terms. First term we can throw away in the first pass, it's negative, so we can throw it out. Second term has exactly the form of a commutator term. So the second term, I'm going to be able to control it by f, by this theorem, that's this functional inequality called commutator estimate. And this way you get dtf is going to be controlled by integral of f. And essentially, because the relative entropy has a sign, and Fn almost has a sign, then you can just control the whole thing. You can control this by the whole thing. And then you're done, right? Grand val and blah, blah. Another remark that we made is that when you write Fn, so the way it was defined, you remember there was a 1 over theta relative entropy with respect to mu plus integral of f you can do a little bit of algebra and observe that it can be rewritten as the relative entropy with respect to q and beta of mu, plus a constant term, which is the log of the partition function. I think it gets divided by n, if I'm not mistaken. So there is another interpretation, in some sense, of this modulated free energy. There is a minus n, sorry. Okay, so it's this. Minus n times this. What you can show is actually that this thing is negligible. It's small for what you want. It's much less than n squared, which is what you care about. And so up to a constant, this modulated free energy is just another relative entropy, except that instead of comparing your distribution Fn to a tensorized distribution, so to an IID law, mu tensor n times, you compare it to a law with interactions. So this q and beta is the IID things, but with interactions, with the repulsion in it. And this is, in some sense, a better representation of the system than the tensorized state. And so this is what you're comparing to. And with that, you can make the proof. And ideally, in business like that, when you see an inequality like this, you want to take advantage of the negative term, not just throw it out. So what would be very desirable would be to have a bound from below for the relative Fisher information in terms of, say, the relative entropy, or in terms of the modulated free energy. Because if you could have a bound from below, then with the minus sign, you would get a bound from above of the form. Okay, so the relative Fisher dt Fn would become smaller than minus c Fn plus other things. You'd get a minus sign here. And if you get that, this is much, much better because now Grandval's lemma gives you exponential decay, not just exponential growth in t, but exponential decay in time, and you would have convergence, fast convergence to equilibrium, etc., etc. So you're left with this question: is it true that this relative Fisher information is bounded below by a relative entropy? This type of inequality is another functional inequality that would be called modulated. We call it modulated because of this relative stuff, but log Hardy-Littlewood-Sobolev inequality. So people have proved Hardy-Littlewood-Sobolev inequalities or log Hardy-Littlewood-Sobolev inequalities, but not in this context where we have this very non-convex interaction. So the problem with our Coulomb interaction is that everything's very non-convex. So a lot of things that are available in functional inequalities are not true here, probably not true. So the only thing we're able to prove is in certain cases in 1D. In 1D, when you have a confinement potential which is convex, then such an inequality holds. And then you can take advantage of the Fisher information term to get also exponential convergence, exponentially fast convergence. Okay, other than that, it remains a sort of conditional result. If you had an inequality, you could get things like that. So there's works of Guillain in particular and Lebris and Montmarché that have exploited such relative Fisher information terms in the context of the relative entropy method. So just the relative entropy without this part. When you differentiate in time, again, you get a relative Fisher information term. And in that case, because they have the tensorized measure in the denominator, it's much easier. You can actually have the inequality you want and deduce negative exponential convergence. So you see, when you have a negative term here, then what's very nice is that the convergence rate becomes uniform in time. It doesn't blow up in large time, and that's much more desirable, of course. Okay, so there's many open questions related to these things, in particular to the sort of geometric structure or functional inequality structure that's underlying these Gibbs measures. But that is all for today. And tomorrow, so there's 3 more lectures, I'm going to go back to the study of the Gibbs measure. Tomorrow will be devoted to local laws and central limit theorem for the fluctuations around the empirical measure, of the empirical measure, fluctuations around the equilibrium measure. And the last session will be about proving a large deviations principle at next order. So we had a large deviations principle at leading order. Now we want to go to the next order and to understand really the microscopic behavior of the points, and in particular something that connects us to these crystallization problems that I mentioned in the first lecture, like whether at low temperature things are going to look like a lattice or something crystallized, will be a little bit accomplished by this large deviations principle. So if you have any questions on today, go ahead. Yeah.
So can you also consider like other distance, for example, the total variation?
So the total variation you can control by the relative entropy. So then that's good. As soon as you have the relative entropy in there, you control. If you have just the Fn, then you have a different distance. It's not as strong. But yeah.
So the modulated free energy method can also improve other proof to like uniform convergence.
So in some cases, yes, we've been able to obtain uniform convergence in time by a different trick. So it's not a functional inequality. It's that when you differentiate in time the Fn, you get the commutator estimating, and if you remember, there is a Lipschitz norm here. Okay, so if you're able to show that your limiting solution has a decaying Lipschitz norm in time, then when you do your ground value, you get actually something better, and you can hope to get something convergent in time. So this is work we did with Matt Rosenzweig. So a lot of what I discussed today has overlap in the work with Matt. And so this is it becomes a PDE study again. You have to look at your PDE and you have to see that there is decay. So when there is noise, it helps you to get decay. When there is no noise, it's a little tricky. But in some situations, we're able to show that this thing decays faster than 1 over t. You need a little bit more than 1 over t so that it's integrable in time. And then you can get uniform. Yeah.
And the Coulomb equation have some discrete gradient flow approximation, like JKO stream.
Yes. So, good point. Something I could have mentioned is that the limiting PDE is a gradient flow. Okay, so this equation. You can view this equation as a gradient flow in the Wasserstein space of probability measures W2 gradient flow. So if you're familiar with that framework of Otto, Jordan, Kinderlehrer, Otto, Ambrosio, Gili, Savare, you can write a lot of continuity equations can be seen as gradient flow, because in fact here what you have is the gradient of the functional derivative of the energy, right? So I don't know, call it E maybe. Right, so if you define E, yeah, it's E. I defined E on the first day, right? So if you define E this way, this is the functional derivative of E with respect to mu, it's grad H mu. So as soon as you have an equation of the form dt mu equals divergence, gradient, functional derivative times mu, it's the 2 Wasserstein gradient flow of E. That's more or less the definition. And so you can have a discrete approximation for it, yes.
So even for high dimensional, it's still correct?
So what do you mean high dimensional for?
So for DA3, is it also the discrete gradient flow also converge to this?
So if D, well, for me, D is fixed and n goes to infinity, right? Are you thinking of letting D go to infinity?
Yeah, yes.
Yeah, so that's trickier. I'm not sure. I think formally yes, but it becomes much more delicate to do things in this setting. So, maybe these things has some reminiscence for people who are interested in stochastic gradient descents, right? You have points, you let them flow in a landscape, in an energy landscape with noise. But typically what people want to do there is they want to do it with D much bigger than N. Right? They want to be in very large dimensions, and they want to sample with some points, but not too many points. And so, yes, it would be very nice to be able to say something. But for us, of course, all the error terms we have are things like that. So it's not ideal. But so if you follow very carefully the estimates in their dependence in D and N, I think in some cases you can say something, but you'd have to be attentive to the details. Anything else? Okay. Thank you.